Bromination of an alkene. In the previous experiment, you learned how to use recrystallization to purify a solid compound and how to perform a melting point analysis to characterize that compound. In this experiment, you will perform a reaction, the bromination of an alkene, and then you will use the techniques of recrystallization and melting point analysis to purify and then learn something about the resultant product of that reaction. A reaction mechanism is a step-by-step diagram of how bonds are formed and broken during a chemical reaction. These mechanisms show how electrons move, not how atoms move. If you are concurrently taking Chem 232, you will have been recently introduced to reaction mechanisms in the context of substitution reactions. You will not yet have covered bromination of alkenes. That's okay, in fact that's actually ideal. This experiment will show one way to identify the mechanism of a reaction when we don't know what the mechanism is yet. The understanding of a reaction mechanism is important. By understanding the mechanism, we can make changes to the reaction conditions in order to do things such as optimize the yield of the reaction and increase the purity of the product of the reaction. Mechanism determination is a non-trivial problem. It is often quite difficult to see what the starting material turns into as it goes from starting material to product. Tools that are available to organic chemists when determining the mechanism of a reaction include using spectroscopy to view intermediates. During a reaction, intermediates tend to not last very long, but oftentimes we can use things such as infrared spectroscopy or NMR spectroscopy to view those intermediates before they disappear. We can use kinetics to see how changing the concentrations of various reagents affects the rate of the reaction. As you saw with the absolute configuration determination experiment, the concentration of base had no effect on the rate of the reaction. What that tells us is that the base is not present in the rate determining step. The base not being used in the rate determining step tells us something about the mechanism. Another tool we can use is an analysis of product distribution. If we have two potential mechanisms, and mechanism 1 provides one product, and mechanism 2 provides a different product, if we can identify which product is actually made, we can identify the mechanism that is what we call operative in the reaction. And it is this type of analysis that you will be performing in this experiment. You will perform a bromination reaction on an alkene. There are several potential mechanisms for this reaction. By figuring out what the product of the reaction is, you will then be able to determine the mechanism of the reaction. If you are concurrently taking Chem 232, you will not yet have discussed the bromination of an alkene. As a result, we will discuss only the fundamental aspects of this reaction. In a bromination reaction, you have an alkene, such as this one here in the bottom left. This alkene reacts with bromine to attach a bromine atom to each carbon that had been part of the alkene. Notice how the double bonds in the phenyl ring are still present. Remember what I said at the very beginning of this course. Alkenes and phenyl rings undergo different chemical reactions. The solvent in this reaction is acetic acid. The presence of acid helps accelerate this process. Molecular bromine, Br2, is quite toxic and quite dangerous to handle. As a result, we will not be using molecular bromine itself. Instead, we will be using pyridinium tribromide, which you can see here in the upper left. Pyridinium tribromide is a salt that is quite stable and much less dangerous than molecular bromine. When you take pyridinium tribromide and you dissolve it in a solvent, such as acetic acid, pyridinium tribromide in an equilibrium forms pyridinium bromide and molecular bromine. Now the key here is this is an equilibrium process. The equilibrium greatly favors the left side of this equation. This means that we have only a small amount of molecular bromine present at any given time. If we only have a small amount of molecular bromine present, will this reaction be slow? Well, no, because remember Le Chatelier's principle. If we take this molecular bromine and use it in the bromination reaction, the equilibrium up here has to shift to the right in order to make more bromine. To recap this slide, molecular bromine is quite dangerous. Instead of using molecular bromine, we will use pyridinium tribromide, a salt. When dissolved in solvent, this salt produces pyridinium bromide and molecular bromine in small quantities. However, enough molecular bromine is present to allow the bromination of this alkene to occur. As the bromine is consumed, this equilibrium shifts to the right to make more molecular bromine. The particular alkene you will use is what is called transenamic acid. There's nothing special about this particular alkene, it is just an easy-to-use reagent. The question in this experiment is, by what mechanism does this bromination reaction occur? There are three potential mechanisms that we can propose for this reaction. The first is a mechanism that proceeds through what we call anti-addition. Anti means that the bromine atoms attach themselves on opposite sides of the double bond. If you have trouble visualizing this, don't worry, you will see an example of this on the next slide. The second potential mechanism is one that proceeds through what we call a syn addition. Syn means that the two bromine atoms are added from the same side of the double bond. And then finally, the reaction could proceed through a mechanism that produces a mixture of both anti and syn additions. You are going to figure out which one of these mechanisms is the correct one. And you will do this through analyzing the products of the reaction. Here on the slide, we see the product of this reaction, the dibrominated compound. What we haven't drawn, however, is the stereochemistry on this molecule. You know that each carbon atom the bromines are attached to is a stereocenter. And it turns out that each proposed mechanism produces different stereochemistry. Let's see that now. Possibility 1 was anti-addition, and if you recall, anti means coming from opposite sides of the double bond. Here we have the bromine atoms, where this bromine atom on the left came from the top of the double bond, and this bromine atom on the right came from the bottom of the double bond. Because this is not an enantioselective reaction, if mechanism 1, possibility 1, is the correct one, we would expect to see this compound plus its enantiomer formed in the chemical reaction. Possibility 2, the syn addition, would produce this product, where both of these bromine atoms came from the top of the double bond. And as with possibility 1, because this is not an enantioselective reaction, we would make this compound and the enantiomer of this compound if mechanism 2 is the correct mechanism. And finally, with possibility 3, if the mechanism is a mixture of syn and anti-addition products, then we will see a mixture of all of these compounds. To recap this slide, each potential mechanism produces a different product mixture. If we can identify which product mixture is actually made as a result of the reaction, we can identify the mechanism of the reaction. The procedure for the experiment is operationally quite simple. You will take your alkene, your transenamic acid, and you will dissolve it in glacial acetic acid. At room temperature, this is a slow process, so you will use some gentle heating to make it dissolve faster. Once all of the transenamic acid is dissolved, you will then add your pyridinium tribromide to your reaction mixture, and then boil the solution for 15 minutes. Note, this is not heating for 15 minutes. You start the 15 minutes once it begins boiling, not once you begin heating. After the 15 minutes have passed, you will allow your reaction mixture to cool, and your product will precipitate out as the mixture cools. You will collect your product via a vacuum filtration. You will then take another technique, recrystallization, and purify your product. And finally, once your product is purified, you will analyze the product via a melting point analysis. And through that analysis, you will identify which product you have. You can do this because each potential product has a different melting point. The anti-addition product, possibility 1, has a melting point of 202 to 204 degrees Celsius. Some of you might be thinking, but I have a mixture of this compound and its enantiomer. Shouldn't I see a melting point depression? The answer is no. Enantiomers of a compound do not act as impurities. Therefore, even though I have a mixture of enantiomers, I will still see a narrow, non-depressed melting point. Possibility 2, the syn addition, has a much lower melting point, 93.5 to 95 degrees Celsius. Remember, the reason that possibility 1 and possibility 2 have different melting points is because they are diastereomers. Diastereomers do have different melting points because they are different compounds. Knowing that, what would you expect the melting point for possibility 3 to be, where we have a mixture of syn addition and anti-addition? You should think about what melting point would be reasonable for this situation. This is the first experiment where you will perform a chemical reaction and then isolate the product of that chemical reaction. When making a new compound, it is important to assess how effective that reaction was. The percent yield of a reaction is a measure of how much product we actually made compared to how much product we should have made based on the amount of starting materials we use in the reaction. In short, it is our actual yield, what we physically have in our possession at the end of the reaction, over our theoretical yield, what we should have made based on the amount of starting materials we used. Remember, to calculate the percent yield of a reaction, you have to identify the limiting reagent. The limiting reagent is the starting material that gets used up first. It limits the amount of product you can make. When finding your limiting reagent for this experiment, assume that all pyridinium tribromide turns into molecular bromine, Br2. You first learned about percent yield in general chemistry, but it has been a while. If you would like a review, you can see the optional webcast I have put up on the course website. In this experiment, you will be expected to determine the limiting reagent of the chemical reaction and then calculate percent yield. To recap this webcast, reaction mechanisms show how bonds are formed and broken during a chemical reaction. One way to elucidate or determine the reaction mechanism is via analysis of the reaction products, and this is what you will be doing in this experiment. There are 3 potential mechanisms for the bromination of an alkene, and it turns out that each mechanism leads to a different product mixture. If you can identify what products are made in the reaction, you can identify the mechanism of the reaction. You will determine which mixture of products was made from the chemical reaction after purifying the product via a recrystallization and then performing a melting point analysis.